Yep. All right, well, good morning, everyone. How did it go yesterday in the lab? Okay, did you manage to get things running? Okay, good. You never know when you have 30 people trying to use the same cluster at once. There might always be some unexpected distributed problems, but happy that that went smoothly. And as I said yesterday, we almost finished, but there were a few slides left here, so I will kind of quickly finalize what we had here with basic Spark, and that should also serve us to review a bit the elements that we have learned yesterday. Again, Spark is a framework for doing large-scale parallel computing, and the base idea is that all the elements that we are going to be processing are RDDs. They are distributed lists that they are spread over our cluster. And we cannot directly access them, but we can order Spark to transform them in newer and newer elements. We finished yesterday, for instance, with this example of a log browsing in which we start with lines of text. We select by filtering only the ones with errors. We map them so that for each line we only keep one specific field that we care about. And there is also this cache operation, this persist operation, that it will tell Spark to keep this RDD in memory after the first time it's been executed. And thanks to that, we will be able to, in this first iteration, when we want to count how many of those elements contain one specific text, all of those transformations will need to be executed the first time. So quite a few operations we will read from the file system. We will create errors from lines, messages from errors. But from that, we will bring back the response to our driver. And in a second step, if we want now to check about a different string, a different text appearing in my data set, this second iteration with this second action will execute way faster, because cache messages will have been kept here in this cache space for each one of our elements. But of course, if we are keeping it here in memory, we need to be careful, because that's going to be some resource that is going to be filling the available RAM for all the machines that we have in our cluster. Okay, this is a quite straightforward program, again, like the ones you saw yesterday. And for many of those programs, you have probably seen that Spark can be used as a kind of a scripting language. It allows us to do some interactive exploration of our data. We can select different elements, we can perform some computations, get the results back to the driver and compare again. But of course, we can also define some batch programs that they have been created in one Scala file, compiled, and that we are submitting to the cluster in order to get some results back. We have not used that in the labs because it makes more sense for a lab so that it is actually interactive, but just keep in mind that that's a possibility. And to show a bit more of how we can express some more interesting algorithms with Spark, here is an implementation of the estimation of logistic regression for a data set, a collection of points. So here at the top, we read from a text file a set of lines. Each one of those lines is a different point with a value for x and a value for y. And we basically map them with this function that is in charge of parsing that format and creating one object. And again, this cache element is quite important so that we make sure that this data set that we have here is going to be kept in memory. And what you see here, those 6 lines of code are an example in how to implement one actual algorithm in which we have iterations, and we are going to successively recompute our estimation of what's going to be the gradient vector for the points that we are computing. And this is a much more interesting example for an Spark problem, mostly because here we actually have to keep in mind the game between the driver and the cluster that I was mentioning yesterday. If you check the code that we have here, and if we use the whiteboard as the representation of what we have here, again, we have two parts of our program. We have the driver program, which could be the computer in the ITL that is executing those lines, but then we also have the cluster. And the first thing we are telling to Spark is that we are creating a data variable that is being created as an RDD, because we are running this text file method that we have used yesterday. So this data element is something that is going to be somewhere here in the cluster. So whenever Spark decides to execute that first line, that will tell Spark to materialize this distributed collection across the machines of our moonshot cluster in this case. The second line that you can see here is telling us to create, is telling Spark to create a vector of random numbers, and we are calling that W. But when you see here the code for creating that vector, there is no mention to Spark. This is a predefined class for the base programming language, for the Scala, and we are not taking an RDD and transforming it into something else. We are simply creating a vector of a defined dimension that we have here. That means that that W variable, oops, this one died. Let's try blue. Yeah. This W vector is a collection of values that exists in the same local program that is controlling the Spark execution. And that's something that can be very misleading with Spark, because all the code looks roughly the same, but actually this is an RDD which is only accessible in the cluster, and this is an actual variable, an actual set of numbers that they are available in our local program. And basically, if we want to do some computation, we can ship variables so that they are arguments for our cluster functions. We can suppose that those elements are going to be very small, so we can easily copy them here. But if we want to get anything back from the cluster, from our RDDs to our driver, we can only do that with one specific set of operations, which, if you remember from yesterday, those operations are called actions. So if we run a transformation here, all the transformations are going to take this RDD and create a new RDD. But we cannot escape this space. The moment we want to get some results back, we will need to run an action that gives us back some values to our driver program. And this is actually what you can see that we are doing here in the main implementation part of this gradient descent. We have a for loop. This is the syntax of the for loop in Scala. And from 1 to the number of iterations that we have defined, we are going to be doing the same set of operations. So here, once we have created W, we basically have a for loop that is going to be executed a set number of times. What do? We are going to obtain one result in a variable that is called gradient. And what is this gradient? Well, in order to see what is this gradient, I need to follow here the set of operations that are being executed to obtain that value. First, I start with data, and I map data, which means that I am applying a transformation, right? And if I am applying a transformation, whichever is the result of all this map function, that it does implement some summatory in which we take each one of the points here and we basically process them with the W vector that I am supplying from my driver. the actual result of that, what it will be? Will it be an RDD or will it be a local variable? If you only look here at this map element. RDD? Yeah, right. Map is a transformation, so if we are actually running not a standard transformation but this very long map, we are actually obtaining here another RDD. We are not giving it a name, but we know that this is again some information generated in the cluster. And once this RDD has been computed, we are actually reducing it. And if you remember, and this was a bit misleading, when we reduce one list, what we are actually doing is invoking an action that takes the whole list of elements and compresses them into a single result that we want to obtain. And here, this code I took from the initial set of slides that the creators of Spark use, and they are using this short form notation for defining a function. Basically, if what you have is underscore plus underscore, this is exactly the same as saying I have two values, A and B, and the result that I am going to obtain is A plus B. So they tend to like this syntax because it's very compact. I tend to use that one so that it's a bit more readable. So I am reducing all those elements. I am basically summing all those partial values. And then this gradient value that I have obtained here, this gradient, is actually one local variable that I have obtained back to my driver program. And that's how, in many cases, you can implement some algorithms in which you are performing computations with large data sets, but then the actual results, the features that you obtain, the set of final result points, are small enough that you can actually bring them back to your driver program. And in this case, this is an algorithm for estimating iteratively what is the right gradient for this vector W. So we adjust W so that we decrease it by the points we computed, and then we start again this loop. And if we start again this loop, we have updated the value of W because we remove this value, and we start again, which means that we forget about those elements that were created in the cluster. They have not been cached, so they are gone. And then we start again. We take the same immutable RDD that we have at the start with our points, and we map it again. We map it again. This is also has no ink. And we map it, but now we change the actual input vector W that we are giving here, because this W has been updated in the previous step of my iteration. And by running this again, and by running that again, we are going to get, so we have our second, our second application of map. This map includes this new version of W, and then we will get an updated version of this vector that we can reduce to a new value of gradient that we can keep using for applying that adaptation. Okay? And this is a much better example into why something like Spark is perceived as a much more expressive and powerful language than MapReduce or Hadoop in order to implement algorithms, because it does allow us to actually create almost any type of sequential looking flow for our program. And what it is going to be able to do is to take some of our data elements, some of our collections that they are large enough, and we can execute in parallel map style operations, that they are embarrassingly parallel operations. We can apply the same function independently to each one of those elements, or we can also efficiently reduce all those elements to a single value. And that way we can actually express quite a few mathematical operations and computations and take advantage of the resources we have in a cluster. Okay? But yeah, if you just look at the code without thinking a bit, it is not obvious unless we are careful to see which elements are part of the driver, which elements live in the cluster. And one important point that might be misleading is that whatever we have here in the driver, those are standard variables. We can do whatever we want with them. But the elements we have here in the cluster, our RDDs, first, we cannot read their values. We don't know what elements they contain. We need to run an action for that. And they are immutable, which means that here, if you see this data that I loaded initially, this is going to be the same data until I go to the end of my algorithm. I can, yes, generate some newer RDDs for partial computations, but at any point I can never actually modify one RDD so that I overwrite it with different values. Sometimes that is not how we think when we are actually implementing some code. So again, as part of this divide, it's quite important to be aware of that. Yep. Okay, I'm taking quite some time. So I'll just do some final closing remarks of Spark in general. And the main thing that I will take here is that Spark, again, is a very powerful language. We can kind of express whatever we want, but giving us choices to express things, to define computations, doesn't not mean that we actually should do that. And this is basically one of the main dangers, one of the main problems that we can get with Spark. We can use methods like this cache method to persist elements in memory, but whenever we are actually writing programs with this model, it is quite important that we are always aware of how large the actual data sets that we are dealing with actually occupy. And not only that, but also what is the difference between different types of operations that we might be actually running. If I go back to a slide quite some time ago that was, that was showing the different types of transformations, yeah. Here we are. The different types of transformations that we can run in a Spark program. I was mentioning that computations like a map, a filter, they are very efficient in general because they are done independently to each one of my elements, and there should be no big communication bottleneck that slows my computation down. But the moment I want to do group by, reduce by key, which is a more complex version of this group by, or something like a join, those operations can easily take a long time. And there are some tricks sometimes, there are some mechanisms of Spark that I have not mentioned that allows us to control how my RDDs are distributed, how many partitions my distributed list has, or how does Spark decide which node controls if which of my partitions, which can actually help quite a bit. And in the case in some operations like this join, it's actually possible to join two different elements and making sure that the elements with the same key, they are collocated in the same nodes, in the same elements. And thanks by doing that, even if the initial code should work in theory, if we really want to get good performance from Spark, it is quite important that we understand the implications of our operations and also the actual basics, the actual sizes of the elements that we are handling. Well, again, we could be speaking a lot of time of that. I just want to kind of give you the full spectrum, because I know that those programs look relatively clean and relatively easy, but when you are actually using it with some real data sets, when you have some good enough size programs, you will quite often find that your program suddenly crashes with apparently no reason. And then is when you actually check things back, you will actually see that what you were trying to do, it's not something that the cluster that you have can actually support. Okay. Any final question about Spark? Okay, then quite late, but we can finally start with our second topic of the week. And now that, now that all of us should be familiar with how we are approaching different problems when we want to use one of those big data frameworks, which is basically we are going to have very large data sets, and we have seen that those type of platforms allow us to automatically apply some limited set of transformations of operations in parallel over the whole data set that we have. And what I'm going to try to do today is first to provide some quick introduction to graph analysis, and why is this such an important topic. I am sure that many of you are actually already using graphs in one way or another, but one interesting thing with graphs is that they are actually a very general purpose, a very natural way of modeling problems, of modeling our domain information. Because of that, it has been applied in lots of different domains, and researchers are usually interested in different types of graphs and different types of problems. So I want to spend the first minutes of today just giving a general overview, in case you are not familiar, of the type of things that researchers are routinely doing with graphs, and then we are going to get into how to actually express graph algorithms. I want to start with the way we usually think more naturally, so sequential style programming, one instruction at a time, and from that I will try to show you why in the case of graphs those type of algorithms usually are impossible to parallelize, and then we need to look for alternative ways of expressing our computation, and finally I will briefly introduce the Spark library that implements some of those parallel graph processing ideas. So, well, what about graphs? Why is everyone interested here? And we are running this week and you have signed up. Again, the answer is that graphs are really used everywhere. Graphs don't really exist. They are just an abstraction that humans have found out, but they are extremely useful for modeling any type of relationship, any type of interaction, and performing some analysis on that. They have been applied to the internet, to modeling social networks, to quite a few biology and medicine settings, for image processing, of course. So, first of all, some basic concepts, some basic definitions that we should be aware when we are talking on graphs. And well, I think all of you will have seen this quite a few times, but when I'm talking of a graph, I am talking of two sets of elements. I am talking of a collection of nodes or vertices that present the dots in my visual representation, if this was visual, and we also have a set of edges, links that interconnect pairwise all those elements that compose my system model. And that is the most basic structure, the most basic elements that appear in any type of graph. Of course, that only represents the actual structure that we have. It is very common in almost every domain that either my vertices or my edges, they are going to have to host some additional data. We can keep some values, some variables, some numbers in each one of my nodes, or possibly in one of my edges, in order to model properties of that domain that I am actually addressing. And well, there are lots of graphs depending on the types of properties that we have. Some of the typical classifications that you could see is the divide between directed and undirected graphs. Basically, in a directed graph, all the edges, all the relationships are symmetrical. And if we go to the social networks world, one example of a directed graph is the Facebook friendship graph. If I am friends with you on Facebook, you are also my friend. That cannot be a directional relationship. Whereas if we go to a different social network, I go to Twitter. In Twitter, I can be following many other users, but that does not imply that those users also follow me. And that's why we could have either directed or undirected edges. There are, again, lots of graph concepts. Some of the basic ones are, for instance, the degree of a graph, the degree of a vertex in a graph, which basically counts how many edges, how many links are connected to that specific element. And it's usually a very meaningful metric because it tends to tell you how important a node, a vertex is inside the overall graph structure. If you have, again, social networks are kind of easy to give examples for. If you have something like Twitter, people definitely know that the more followers an account has, the more relevant, the more important that account has. And that goes up to the point that a celebrity like Paris Hilton with millions of followers can be paid thousands of dollars just to retweet something, because the actual effect of that node in the network doing something is way higher than the effect that my account would have if I retweet the same message, the visibility that you get. There are other concepts like a diameter, which is basically the longest path that we can find out the maximum distance between any two nodes in my graph. And that gives us an idea of how spread out or how dense my actual structure is, how long it can take me get from any point to the other point in the network in the worst case. And quite a few concepts, paths are across the network, walks, and even random walks that try to traverse the graph by going randomly to one point to another. Plenty of different elements. And again, one of the fields in which graphs have really exploded and have been a natural fit for performing analysis of what's going on is definitely social networks and social graphs. One thing I want to use social networks as an excuse to point is that, again, when we are talking about graphs, graphs do not exist by themselves. They are simply one abstraction that we decide to create. In the case of a social network, we will have contacts, we will have accounts, we will have messages, we will have the content of our messages, possibly Twitter hashtags. And depending on what we want to analyze, we will say which one of those elements should be mapped so that they become nodes, which of those elements are telling us about the relationships between those nodes, among those edges. And exactly with the same information, we could actually be building many different graphs, and each one of those would allow us to look about users. Other graphs would allow us to look at how different topics are spread across our network, to give you another example. And well, this is, again, social graphs are in general very well known. I wanted to, again, very quickly give you a few examples on how different people have been looking at graphs and why that's actually something useful in many different research fields. And one of the main things that lots of researchers have done is to have a look at the global properties of the overall structure of some graph that has been constructed from some infrastructure. Like, for instance, I belong to the networks group here, and network researchers are really interested about networks because any physical network, it's directly modeled as a graph. We have routers, we have edges, and there have been quite a few studies that they build a graph from what are the actual interconnections that we see in the network, and then see what we can actually learn from that. And one extremely influential paper from 15 years ago from Christophe Falotsos, which is quite common, quite well known in many data mining fields, found out a general property of many graphs that can be built from infrastructure created by humans, which is this idea of a power law in the distribution of degrees across a network, which basically means that some of our nodes, the most common, the most popular nodes, are going to have a very high degree, and that degree actually decreases exponentially as we keep looking at the other nodes in the network that are a bit less popular. And if this is exponential and we draw a plot in a log-log scale, you will see that many networks actually have this linear look here. And it's quite interesting because this type of behavior happens here for how the network is interconnected, also happens with how people consume content. If you look at YouTube, if you look at other content generation services, it also applies by how people browse at the different elements in eBay or any type of shop. So there is something that researchers have found that we humans, in many different contexts, seem to actually fit, strangely enough, kind of a nice distribution. And in other type of analysis, for instance, some Facebook engineers applied, again, build the full forensic graph with 1 billion nodes of everyone who is connected to this social network, and they were looking at, okay, how do users look like? Let's try to also do a user-specific analysis to get an idea in how each one of us is. And they, by simply looking at some of those basic concepts, again, like the degree of a user, and the degree of the neighbors of that user, that means the friends of one account, they, for instance, show something like that. If this is the diagonal line that you have, well, you can see that if you have a user that has not too many friends, here the degree is equivalent to the number of friends that we have, well, for users that they are not too social, like myself, I don't really like Facebook, well, even if we are not social, you can see that the average degree that my friends has, they are way more social than me. So it does not mean that if I am an asocial person, I only have asocial friends. Those very popular, those very high degree, well-connected nodes, they show connection almost with everyone, also with asocial users. Although, as I become, on average, a more social user, also it seems that, on average, my connections tend to also be more interconnected. Another study, another quite actually news highlight that they found out in that study was about how well connected we are in a network like Facebook. How many steps, how many degrees of separation, if you know about that theory, do I actually have with every other user in the network? There is a quite popular hypothesis called the 6 degrees of separation hypothesis that says that in any human network there is at most 6 steps between any of us and any other person that actually belongs to the same network. I always know someone who has been talking to someone who once worked with someone who knows the person I would like to connect to. And when they actually did the study for the actual Facebook graph, they found that if you look at this continuous line of the global Facebook graph, you can see that this is 80% of the users, and this is a distance of 4. So you can see that roughly more than 70% of the users of Facebook can reach each other under 4 hops of distance. And if they actually go with the actual average, they found out that the average degree of separation in Facebook is only 4.7. So it is really a very closely connected network. These type of studies have actually gave a lot of prominence to a field of research called complex network research, in which many physicists, not only computer scientists, but lots of physicists and mathematicians have got into this area, and they basically are interested in finding new interesting properties of some of those graphs so that we can actually learn some valuable insight from those properties. And it's kind of an interesting divide, because you have people figuring out new ways of expressing computation or expressing properties of those graphs, and then we keep applying that to more and more domains, to infrastructure domains, social domains. Some of my colleagues are also working on ecological networks and animal networks, seeing how those properties translate or not. So just looking at the actual structure of the graph is a very active field from many researchers. Another example, and possibly the most important graph algorithm for the history of big data, is the PageRank algorithm that Google invented. Many people think that this is the reason that Google became such a breakout success. When Google started, there were other web search engines. Possibly many of you were not really browsing at that age. I think you are maybe a bit young, unless you were very early adopters. But there were other search engines. There was this Alta Vista system that was actually great, until Google came and basically swept over all of them. And at that point, Google was just a search engine. Why did Google win the search fight? Because their search results were way more relevant, way more useful than anyone else. And the key for Google results being so good is thanks to this PageRank algorithm. And PageRank is actually a graph algorithm. When we are searching for web pages, we are only typing a set of search terms, but what PageRank does is it takes any actual graph, any actual network, and it basically computes one ranking for all of the nodes in the network. We don't need to go to the details, but well, I recommend you check the paper if you are interested, because it's a quite important historical piece of graph analysis and actually how the internet has evolved. But the main idea of PageRank is that we start with a graph, and initially we say that all the nodes are equally important. But what we are going to do is, for each one of the nodes in our network, we are going to give part of our importance to the other web pages that we are linking them to. So each one of the nodes is one different web page, and in order to compute PageRank, we basically share our PageRank score to evenly between the nodes that we are linking to. And because of that, the more central a node is, the higher amount of incoming links, the higher in degree that a node has, the more PageRank score it will actually collect. And you can definitely think that something like the Wikipedia, which is almost these days a universal way of finding an explanation about any topic, is going to have lots of incoming links, because when people want to cite something in any web page and they want to tell you to learn more, they will just link there. Well, thanks to that, as the Wikipedia is a receiver of many links, and it does not have too many outgoing links, although it's got a few, it will be one of the web pages that gets a higher PageRank score. And because of that, if you do a Google search, that is going to be one of the websites that always appears on the first page of results, if you are searching for some simple term or definition. So this is an algorithm based on graphs that, again, it has had enormous impact actually in how the web really has evolved. And it is actually very straightforward. It is an iterative algorithm, if we model it as a graph algorithm, and in each one of the iterations, every node is going to be sending the PageRank score to each one of the neighbors, and then its neighbor is going to update the PageRank score thanks to the actual contributions that the local nodes gave, plus some coefficient that gives us how the probability will be that it still stays in that page. Other examples of main types of graph studies, graph algorithms. Well, one of the most important possibly analysis techniques, we cannot really see the colors here, is in general graph community detection. And the idea of community detection is that when we have a big graph structure, many times we actually can classify, we actually can cluster the different nodes in that graph depending on how they are connected to each other. Again, to give another social example, if you think of a social network like Facebook, you can definitely expect that people from Queen Mary, for instance, they will tend to form a close community because we frequent the same spaces, so then we are probably going to be much more connected through Facebook than if you compare people from Queen Mary and people from, I don't know, UPM in Madrid, because we are in physically disconnected places. I studied in UPM and I moved here, so I do have connections in both elements, but if you just look at the graph, you can definitely feel that there will be a group of elements that they form, or they almost form what is known as a clique, a set of nodes that all of them are connected to each of them, whereas other group of nodes will also tend to gather this type of connections. There are tens of different ways of trying to approach this problem on how to detect communities. You could be looking at the properties of the graph. You could be looking at the actual attributes that each one of those nodes has, so that you look at nodes that they look similar in some way. And it can also be applied to many, many different fields. For distributed systems, for instance, community detection is a quite important technique, because if we have a large graph and we need to figure out how to efficiently partition it, how to efficiently separate it into multiple elements, if we find and we can do a good classification on those elements into communities, we will be able to cut each one of those communities away, and you can expect that the nodes from that community are going to be interacting much more often, frequently with each other. So imagine that you want to run any of Facebook services, you want to have each user in the same server as all the friends of that user, so that when you load the timeline of that user, you only need to check from that specific server. If everything is spread in any random way, we don't really know what will happen. Other examples of, again, types of graphs and types of analysis could be bipartite graphs, which are graphs in which each one of the nodes, basically we classify all the nodes of our graph into two categories, partition 1, partition 2, and all of the nodes that we have in one partition can only have links with the other partition that we will see at the other side. So, is this a useful way of modeling graphs? Well, it's actually useful in many different scenarios. For instance, it allows many techniques to model scenarios in which we want to track and to follow user browsing behavior or content consumption behaviors, because we can represent users as nodes and content items as nodes too, and model the click of a user or the access of a user to a content as an edge. And there are many techniques that do prediction of where the user will go, what the user would be interested in seeing, or in a more straightforward but also quite real and actually classic mathematical problem, there is this table marriage problem in which we have a bipartite graph with male and female nodes, each one of them with a set of properties, and we need to figure out what is the optimal matching so that all of them will actually be as happy as possible. And Well, there are many websites for matching companies, jobs from companies to job applicants, dating websites, where again, this type of techniques can be quite relevant. Final example, and that's been quite a few, graphs are also in general very useful as a way of modeling and getting a hold on how information looks like. And in particular, there's been in the last 15 years a lot of interest for property graphs. If some of you have heard about the semantic web, the link web, or RDF, what all those names and technologies have been proposing is to basically model all the knowledge, all the data in the internet, in the world, as a structured graph in which we can basically have nodes for each one of those concepts, for each one of those elements, and keep extending and enriching this model by having properties of those nodes and also relationships between this person has purchased this book. So we put this actual link between this vertex and this vertex. It was purchased at this date. And there are quite a few graph databases. Oracle is trying to get into this space, but quite possibly Neo4j has been the most popular open source software that has been pushing into this idea that allows us to actually model information like that, keep it in a database, and then be able to query it in an efficient way. And these days, actually, I was reading on the newspapers that Neo4j is actually quite a hot system because it has been one of the components that the team of journalism behind Panama Papers has been using to actually dump all the different connections, all the different actors that have some accounts in with this interesting company from Panama, and it does provide you a very natural way of dumping the data there and then querying it back with some systems like Gremlin. So lots of things about graphs. And after this introduction, let's now get into, okay, how can we actually do something with those graphs? Because I have been talking a lot about applications, but what about the processing that we want to do of graphs? And in order to give a motivating example, I am going to use one of the oldest and one of the most classical graph analysis problems, which is one problem in basically having to explore, having to traverse a graph in order to find what is the shortest path from one source vertex to every other node in the graph. This is extremely important in computer networks so that we figure out how packets will arrive anywhere in the internet. This is also something that TomTom, Google Maps, and all those systems actually use when they want to give you what is the best route from one source to one destination. And for this problem, the classic traditional way in which we have solved it is by using Dijestra's algorithm. Let me do a quick check. How many of you have seen at some point Dijestra's? Great. There we are. So possibly you don't remember the exact details, but this is basically what Dijkstra looks like. We need to first initialize our graph. We have a list of vertices, and we have one estimation of distance per vertex. The source vertex has a distance of 0 because we know where it is. We have no idea of the others, so we set a distance of infinite. And the base idea of Dijkstra is that we keep this extremely important structure, this queue that has the whole list of vertices. And we are going to take this queue and extract one vertex at a time that we have not explored before. The main trick of this extraction is that we are always going to extract the vertex that is closest to the origin. So if one of our vertices has a distance, estimated distance of 1, the other a distance of 2, the others a distance of infinite, we will extract from here in this first round the one with a distance of 1. And then we basically extract a vertex, check all the neighbors, all the direct links of that vertex, and based on where we can get with those connections, with those links, we will update the distance estimations of the neighbors of that vertex. And once we have explored one vertex, we keep exploring another element of this queue and another one until we get a final solution. Why is Dijkstra so popular and why is Dijkstra so used? Well, because it's extremely efficient. Dijkstra guarantees us, and there are proofs that we will get a correct solution by exploring exactly once each edge. We are not wasting any time. So if we have a graph like this one with 3, 5, 10, 14, 18 nodes, we will only have to check once each one of those connections here. We will never have to backtrack. The other key element of Dijkstra is this queue, because all the algorithm is based in having a queue where we are holding all of our vertices and making sure that in each iteration we extract the vertex with the lowest distance estimation. And as long as we do that, we are actually going to get the correct solution. In principle, this is good. As long as our graph is not too large, this is going to work fine. We will have one iteration per node of my graph, but as long as I don't have too many nodes, as I said, this actually can be fine. Okay, that's how many sequential algorithms tend to do. We have a list, a sequence of nodes, a sequence of candidate elements, and we need to figure out a way to explore, a way to actually go and check the results that we are getting in the graph. And Dijkstra tells us the right order in which we should do that, basically. Okay, let's stop 1 second now on the analysis, and then let's take a step back on how can we actually represent our graph. Dijkstra tells us the computation bits, but if I tell you, okay, but I want to implement Dijkstra or I want to implement any graph algorithm, where do I keep my graph? Well, if you are using a programming language, if you are using Python, you could use Network X or iGraph, which are libraries that have a graph object. But if I am not using any of those libraries, how does a graph look like? And that's actually a pretty, that's actually a pretty important point when we are thinking on how those algorithms look like, because we need first of all to save or persist our graphs in some way, and we also need to keep them in memory. When saving graphs, the most common way really to actually represent them is an edge list, so that we have a very long chain of elements, and each one of those lines, each one of those bits is telling us about one edge of my graph. Node 1 is connected to node 4, node 2 is connected to node 3, node 5 is connected to node 2. And then, if this is a directed graph, then this means that the link is only defined that way. I would need to actually define for 1 if I want to express that this is a mutual connection. But this is simple. We actually are mentioning here that implicitly we are defining implicitly here what are the nodes of my graph, because if I have the edge 2 to 3, that means that node 2 exists and node 3 also exists. So in general, this is the most common way in which you are going to be serializing a graph into a file or any kind of repository. The problem with edge lists is that this is not at all the way you want to be holding your data, because imagine that you want to run Dijkstra and what you have is this list of elements here. Well, if you have this list of elements here, first, you don't have a list of vertices. You will need to have that some way, but that is nowhere present here in any way. And also for Destra, you also need to have a set of neighbors for each one of your nodes. And how can I know here which are the neighbors of 1? Well, 4 is a neighbor of 1, 6 is a neighbor of 1. But in order to figure that out, I need to actually scan the whole list. So this is okay for saving information, but it's basically useless for any processing. If we want to do processing, there are two main ways in which we can actually represent our graphs. One way, which will probably be the nicest one for all of you who are used to MATLAB, is to represent the graph as a matrix. We can define an adjacency matrix in which basically we have a square matrix of dimension n, and whenever we have a link, an edge from vertex A to vertex B, we will have a 1 in that cell of our matrix. So if we have the graph that you can see here, which has an edge from 1 to 2, that means that in 1, 2, I will have a 1. Whereas if I don't have a close link from 1 to 1, then I will actually have a 0 here. This is a quite clean way of representing a graph. And if you want to implement something like Destra here, actually this is very well suited for that, because if you want to see what are the outgoing links of any vertex in a system, you only need to check at the adequate row. For instance, I know that 2 has outgoing links to 1, 3, and 4. Indeed, in the graph here, one outgoing link to 1, another to 3, and another to 4. So I can very easily take my matrix, put the right indices for the row and the column, and actually retrieve already what's the actual structure of my graph. So based on that, something like an adjacency matrix is very convenient if we want to implement algorithms. The big problem of an adjacency matrix is that it is a data structure that scales extremely poorly with graphs. And it scales really, really badly because of the problem of graphs in reality being sparse. What does a sparse graph means? Well, a sparse graph is one where the number of edges is way smaller than the number of maximum possible edges, which would be the number of vertices squared. And this is quite obvious. If you look at Facebook, it's got more than 1 billion users, more than 1 billion edges, but the actual average degree, the average number of friends of a user, it will be something like 400 or 500. This means that if we want to model the Facebook friendship graph as an adjacency matrix, this would be 1 billion times 1 billion, but if we look at the first row, we are going to have almost 1 billion zeros. Only 500 ones will actually appear here. And that is the reason why, whereas adjacency matrices are very convenient, and for instance, in the case of some small graphs, and for some type of, for instance, 3D models, kind of synthetic meshes, they can be quite useful. The moment we are moving into large graphs, they are really hardly used because we are wasting 99.99% of the space in just zeros. What do we do then instead, rather than using those matrices? Well, what we basically do in many cases is to compress those matrices by removing all the zeros. And then what we basically obtain is an adjacency list. It's one data structure in which we are going to have keys and values. The keys are going to be the nodes, the vertices of my system, and for each one of the nodes in my system, I am going to list what are the outgoing edges that I actually have there. So node 1 is connected to 2 and to 4. Node 2 is connected to 1, 3, 4. 3 is connected to 1, 4 to 1 and 3. And in this case, they look more or less equally big, but it is quite clear that if we go now to the Facebook case, we will have 1 billion entries here, 1 per node, but each one of those entries will have on average 500 results here. It won't have 1 billion results here. And that means that this is a much more compact way of modeling those sparse graphs. What about processing? Can we use this type of scheme of vertex plus vertex neighbors to implement something like Destra? Yes, it works quite well for that again. If we look at the keys of this list, we again have the list of nodes, and if we want to check for node 4 what are the outgoing connections to 4, we have direct access to that. It is indexed under the node ID. So in general, adjacency lists are almost as good as an adjacency matrix for still giving us quick access to the structure of the graph. The only downside is that when you have an adjacency matrix, you can look at a graph in two ways. You can look at the outgoing links. 2 can send messages to 1, 3, and 4. But you also, in an adjacency matrix, can look at the incoming links. You can see that node 1 here can receive messages from 2, 3, and 4. And if you go here, you see that 1, indeed, it's got an in degree of 3, receives messages from 2, from 3, and from 4. So there are those two ways of actually looking at the graph structure. And this second way of actually processing or traversing the graph, if you want, is lost here. We cannot see what is the in degree of a node, what are the actual incoming connections of a node here in a direct way. We would need to recompute this to generate the complementary adjacency list that models not the out degrees but the actual in degrees of the system. But in reality, for something like this, Destra, for instance, we tend to only need to send information one direction, either everything out or everything in, which means that for many cases, at least, that is the most common way in which we will tend to represent and to actually navigate the structure of a graph. Okay? Well, let's then, I think, make a break here. Let's try to make it not too long, so if we can go back slightly earlier than yesterday, it would be great so that I don't overrun my time. But now we are at the right mindset in which we should be able to see why those algorithms don't really fit then in a parallel computing setting, and how can we look of an alternative way to be able to process the graph in a parallel form.